Thank you very much. Can you hear me? Yes? Very good. So, nice to see you again. So today I'm going to tell you a story, probably two stories actually, if I have time. And the first one will be, as Judith was introducing, about metal organic frameworks and about different promising geometry in frustrated systems. So first, let me introduce you my collaborators, because the story I'm going to tell you is a very nice story of collaboration between chemists who synthesized these metal organic frameworks in the University of Augsburg. So Richard is the student who synthesized it in the group of Dirk Vollmer. Experiments done by Anthony Esche in collaboration with Hans and Philipp Gegenwart. And then theory, both ab initio, DFT, with Alexander Tchirlin, and also like simulations and mean field calculations, field theory calculations in the group of Lode Paulet, with particularly with student Raja Nutake, who is who is doing his PhD. So first, a little bit of geometry. I mean, nothing difficult. Just take 3 points, and you want to put these 3 points at equidistance from each other. And to do that, you can do it in a plane like this in 2 dimensions. That's very easy. You just connect them. And that's the famous triangle that we all know very well here. Now, if you want to add 1 more point and put 4 points at equidistance from each other, you have to do it in 3 dimensions. You cannot do it anymore in 2D. Okay? And that's the tetrahedron that we see in the Pyrochlore lattice, for example, all the time. And these 2 structures, triangle and tetrahedron, are responsible for the majority of frustrated systems that we're studying. Quite frequently with corner sharing triangles or tetrahedra, also sometimes with edge sharing, like for example in the triangular lattice. But you see we have lots of triangular-based frustrated systems in 2 dimensions, and also possibly in 3D when we put them into different orientations, and checkerboard lattice in 2D and Pyrochlore in 3D. So here, nothing new, but it's just to emphasize the fact that, except with there are a few exceptions, in particular the Kitaev system are famous exceptions. Many of the frustrated lattices are made of either triangles or tetrahedra. So 3 points at equidistance in 2D or 4 points at equidistance in 3 dimensions. But the thing is, what if we, I forgot to mention, if you do a quick Google Scholar research, you see that just Kagome, it's more than 30,000 results, and Pyrochlore is more than 60,000 results. So it has been quite studied over the past few years. So I've told you about triangles in 2D, tetrahedra in 3 dimensions. But now, what if you want to have 5 points at equidistance from each other? If you want to have a frustrated units, not made of 3, not made of 4, but made of 5 points. Of course, we cannot go to 4 dimensions. We don't have access to the 4th one. So what we can do is we can ask our chemistry colleagues if they have an idea, and then you can add a 5th magnetic ion in the center of the tetrahedron. So you can see that here in this frustrated unit made of 5 spins, all 5 spins sides are connected to each other. So there are 2 different equivalent bonds, J1 and J2, but they are all connected. So you have one frustrated unit made of 5 sides. And now, I mean, that's nice, but that's just like 5 sides alone. You cannot do, I mean, you can do some calculations, but what you want is a proper lattice. So then you look at the papers in chemistry, and you find that there are a few examples of this lattice made of corner sharing 5 sides unit. Not that many, because this is almost the full literature in chemistry. I mean, I cannot say that I've done a full research in the chemistry literature, but this is really, I mean, almost exhaustive list of the literature on these materials. And as you can see, almost, or so far, nothing on the physics side, not that I have found anyway. And so that means that this structure I'm going to tell you about, made of 5 sides, unit cell, is very promising. It has been studied and it has been synthesized chemically, but we still need to understand the physical properties of this structure. And so to do that, we're going to start with manganese magnetic ions and with the triazolate ligands. So manganese ions, why do we consider manganese ions? Because manganese 2+ that's a half-filled 3D electron valence bond, which means you have a magnetic spin S equal 5/2. So 5/2 is pretty large. That's, to a good approximation, a classical spin. And it's a half-filled band, which means that your system is roughly isotropic. So considering Heisenberg spins will be a good approximation. Then the ligand between them connecting these manganese ions is made of 1,2,3 triazolate, like this. So I will show you the 3D structure in a moment. Our colleagues have done high resolution X-ray diffraction to measure the symmetry of this lattice, and they have found that we have a lattice cubic symmetry. So we have, by lattice cubic symmetry, it means that we have a perfectly cubic symmetric tetrahedron with the center, with the magnetic ion in the middle. So the tetrahedron are not distorted. You don't have inequivalent bonds. All 6 bonds of the tetrahedron are equivalent. I'm going to show you that in a moment. So this is the chemical structure of the material. And so you see that, so the magnetic ions are the manganese ions are the yellow ones and the red ones in the middle here. So the yellow ones form a pyrochlore structure with a central red ion in the middle. And the bonds between these magnetic ions are formed by the ligands. So it's something like this. M corresponds to manganese. And then you see you have a triazolate here, which will connect two manganese ions on the tetrahedron and the center manganese ion here. So this is for the chemical structure, but for us as physicists, all we need to see is that we have a pyrochlore structure with a magnetic ion in the center of each tetrahedron, like this. So we have 2 equivalent manganese ions, but both of them are spin 5/2 with half-filled band. So both of them are very well approximated with the classical Heisenberg spins. Now we have done DFT calculations of this structure, and we have found that J1 and J2 are actually comparable in strength, because in one case, between these two, we have 2 nitrogen ions in between, and between these two, we have 3 nitrogen ions. So actually the path between them is just 1 more nitrogen ions, and that's not a big difference as far as the strength of the coupling is concerned. And so we will see that the ratio of J1 and J2 is actually not so far from 1. But on the other hand, J3 is much smaller. So DFT tells us that, so we know that we have manganese 2+ ions, so we know that we have, to a good approximation, nice classical Heisenberg spins. We know that from X-ray diffraction, high resolution X-ray diffraction, that we have a nice cubic symmetry. So the 6 bonds of the tetrahedron and the 4 bonds inside the tetrahedron are equivalent. And DFT tells us that J1 and J2 are the dominant terms and that we can neglect J3 to a good approximation. And so that's our Hamiltonian, like this. J1, J2 Hamiltonian. And now we have studied this material experimentally. Okay. So here I'm going to show you the different experimental results and the comparison of these results with our theory. So first, the susceptibility, 1/chi as a function of temperature. So we have a nice long Curie-Weiss fit. So the Curie-Weiss temperature obtained is -20 Kelvin with a Landé factor of 2.05, which is consistent, and an effective magnetic moment of 6.05. All of this is consistent with a nice manganese 2+ magnetic ion. And this is also consistent with one previous experimental measurement on this material for the Curie-Weiss susceptibility, which also found something around -20, -30 Kelvin. So this is under control. Then if we measure the specific heat, we find that a function of temperature on the log scale here, the specific heat has a broad bump here, and then a peak at low temperature. And so the peak happens at around 400 millikelvin. So that's a thing to keep in mind. The Curie-Weiss temperature is around 20 Kelvin, and the transition temperature is at around 400 millikelvin, which means the ratio of the two gives you around 50. So for the frustration. Okay, very good. And so we know that this bump here is coming from the quantum coherence, so from quantum correlations in the system. And so, okay. Okay, good. And so we know it's well reproduced by just hexagonalization of a single tetrahedron. Like qualitatively, we can reproduce this bump with just ED of 4 sites of a tetrahedron with the parameters of this material. And so that's what we have done here with 5 sites, of course. And we can reproduce also this bump with 5-site hexagonalization. 5 sites. So this is the first thing. Next, the next thing is this susceptibility. If you plot it as chi susceptibility times temperature as a function of temperature, we see a clear evolution from a high temperature Curie-Weiss fit to a low temperature here Curie law, which corresponds to a spin liquid Curie law. I'm not going to go into details here, but this here gives us many data points to compare experiments to simulations, in particular to classical Monte Carlo. Yes?
What J's are you using?
The values of J couplings. So they are of the order of 15 Kelvin. Antiferro both. Yes. So actually, I'm going to give you that value very soon. But yes. And so we compare the Monte Carlo simulations with the experiments, and we can fit the experiments from like 300 Kelvin down to roughly 1 Kelvin or below. So what we see here are 2 things. One is that the ratio of J2 over J1 to feed this data is of the order of 2/3. So there is only a ratio of 2/3 between the first and second nearest neighbor in this material. And the second one is our simulations do not show the long-range order at low temperature. When you have J1 and J2 antiferromagnet, the low temperature physics in simulations is a spin liquid. So which means that this peak here is beyond our J1, J2 model. So we have some idea about what's going on here, possibly dipolar interactions or things like this. But what I'm going to tell you about today is about a minimal J1, J2 Hamiltonian, okay? And so we have this nice fit here from 300 Kelvin down to roughly 1 Kelvin, a little bit below actually. And if you do magnetization curve, so magnetization as a function of magnetic field at different temperatures, you again have a nice fit with the same parameters from 0 to roughly 7-8 Tesla, and for different range of temperatures. So this ratio of J2 over J1 of roughly 0.67 matches very well with DFT estimate. So the DFT ab initio calculations done by Alexander Tcherlin tells us, so there is some range of degree of freedom about the absolute value of J1 and J2. So depending on the parameters of DFT, we can change a bit that. But the ratio between the two found in DFT calculations is very close to the one we find in classical Monte Carlo simulations. And if we compare it to what we used in hexagonalization, it's not so far either. Hexagonalization is a bit further away, but it's not surprising because this is really a very rough approximation to reproduce the high temperature bump. So we don't expect these parameters to be really precise. But still, ED give us something which is of the same order as classical Monte Carlo and as DFT calculations. And so if we use classical Monte Carlo to study the phase diagram of the system, I'm going to detail it in a moment, but we see that there is a broad spin liquid region here. The manganese parameters are all in this region. So that's a good thing, that even if we have uncertainty about the precise value of these parameters, J1 over J2, we know that they all fit right in the middle of the spin liquid region. Then we know that in experiments, there is a transition temperature, and if we rescale it by the right parameters, this transition temperature happens here, which means that there is this whole region here at finite temperature where we can expect signature of the proximate spin liquid. So we know in the minimal J1, J2 model, we know that this region is a spin liquid. In experiments, we find a transition temperature at low temperature, but we know that at finite temperature, we should see signature of the spin liquid, which means that if we do experiments in this region, here or here, between around like 1 to 2 Kelvin, we should find signature of a spin liquid. And so manganese triazolate is proximate to a spin liquid state. Now, let's study the spin liquid in this model theoretically. We have 5 seats in a tetrahedron with the central spin in the middle. And it's all antiferromagnetic couplings. And so that means that we can rewrite the Hamiltonian this way. This is the same writing that we have in Kagome, in Pyrochlore. This is a famous one, where we write everything as a sum of the sum of magnetization squared. Now, the only difference is that in Pyrochlore system, you will have only this term of the 4 spins. So the 4 corner spins will give you the magnetization of the tetrahedron, and that's all you will have in this term. But now, we also have this central spin here, the green one in the middle, that gives an additional term divided by eta, which means that when eta is very small, this term here will dominate. And since the magnetization, the Hamiltonian is a sum of this term squared, that means that what we want is to minimize the value of this term, ideally to have it equals to 0. We'll see that it's possible for the spin liquid regime, but not for small value of eta. Because what happens is that for small value of eta, this central spin will dominate. For example, imagine that eta equals 0.1, for example. So 0.1 means that J2 is very small over J1. Then for 0.1, then you have this central spin times 10 plus all of this. And you see that since all of these spins are normalized, if you have 10 is here, the sum of 4 unit spins cannot cancel out this one. So which means that this term here will necessarily be finite. And so what will happen is that this central spin will point in a given direction, and all of the corner spins will point in the opposite direction. And you will get ferrimagnetism. Now, as you increase eta, so as you increase J2, this central spin will have less and less influence. At some point, you will be able to have some tilted angles. So this is perfect ferrimagnetism. Here in this region, you will have partial ferrimagnetism. And at some point, it will be possible for all of these 5 spins, even with the term eta, to cancel each other. And so this term here will be equal to 0. And this will give rise to a disordered classical ground state, which is this classical spin liquid, which is a green region that you have here. If we calculate the bond excitations, on the left part of this phase diagram, we have the lowest band has dispersive bands, and the minimum correspond to the ferrimagnetic states. But on the right part of this phase diagram, the lowest band are these flat bands. And the thing is, the number of sublattices in this lattice is 6. You have 1, 2, 3, 4, 5, and the 6th one coming from the neighboring tetrahedron, because you have up tetrahedron and down tetrahedron. So you have 6 sublattices. 6 sublattices means that you have 6 bands. And here you only see 3 of them because the flat band is degenerate 4 times. You can show that exactly, that the flat band of this system of this spin liquid is degenerate 4 times with a gap with a dispersive band. And that means that 2/3 of the bands are flat and correspond to the spin liquid. So from the point of view of the spin liquid, this is a very, very, very disordered spin liquid. For example, Pyrochlore, it's 2 flat bands over 4. Kagome, it's 1 flat band over 3, which means that the number of flat bands with respect to the total one for this one is much bigger than both the Kagome spin liquid, classical spin liquid, and the Pyrochlore classical spin liquid. So this is a very disordered phase. By the way, feel free to interrupt me if you have any questions, of course. Now, what if we want to characterize this phase? The best way, I mean, we are used to it. Spin liquid, we don't have broken symmetry, we don't have other parameters, so we use structure factor. And these are the structure factor as would be seen by neutrons, so they are without the parallel component to the Q vector. So this structure factor, when you are eta equals 0.4, so here in this region you have Bragg peaks. That's long-range ordered. Ferrimagnet or partial ferrimagnet, you have Bragg peaks. Then when you are just next to this, in this region here, you see these diffuse scatterings. And these diffuse dots, this broad scattering, they are where the Bragg peaks of the ferrimagnet were. So they could just correspond to short-range ferrimagnetism. So this region is disordered, but it's disordered in a kind of trivial way, like short-range ferrimagnet. Now, if you go, actually, eta equals to 3, so it's way beyond this. Eta equals to 3 means that J2 is 3 times bigger than J1. So the couplings that matters are the Pyrochlore coupling. Pyrochlore, and so that means that in this limit, you have the Heisenberg Pyrochlore antiferromagnet with a central spin, which is almost uncorrelated from the rest. And so here you recover the pinch points of the Heisenberg antiferromagnet because you are in the 3D Coulomb phase. And now what is interesting is this region in between, because this region in between is different from a trivial ferromagnet. It's different from the 3D pyrochlore system that we all know. And that's also the parameters which are relevant for manganese triazolate. And in this region in between, you have this structure, which is somewhere in between the two. And in particular, you see that the pinch points here becomes kind of broad and diffuse. And so that would be the question of why do we obtain diffuse pinch points? And as a matter of fact, you see the right-hand side correspond to classical Monte Carlo simulations, and the left-hand side correspond to analytical mean field calculations. And so you see that for the spin liquid regime, the comparison between the two is very good. When you get closer to a ferromagnet, mean field is always kind of, yes? Between these two? No, there is no phase transition. It's the same phase. So yeah, so the question was if there was a phase transition between these 2 points, and no. So the phase transition is only this solid line here. This here is not a phase transition. That's a very good point, thank you, I should have mentioned it. This is a crossover, okay? So there is no singularity. This is a crossover. There is no broken symmetry below, and as you move all along, so between these 4 different structure factors, these 4 different parameters, you don't have any phase transitions. It's a smooth adiabatic continuation evolution between the 3 of them. Okay, thank you for the question. So you see that we have good correspondence between field theory and Monte Carlo simulations, except when we are very close to the ferromagnet, because mean field theory are not very good to capture the onset of long-range order. I mean, it's a bit biased here. So, but as long as we are in the spin liquid region, it's working fine. So why do we have pinch points, or broad pinch points, diffuse pinch points? And the reason is coming and interesting. So this is a Schlegel diagram of a pentacoron. So there might be 2 words here that you don't know about. So Schlegel diagram, that's a 3D representation of a 4-dimensional object. And a pentacoron, that's 5 points at equidistance in 4 dimensions. So that would be the equivalent of the triangle in 2D, tetrahedron in 3D, pentacoron in 4 dimensions. Okay? And you see that this Schlegel diagram looks very much like our center tetrahedron. You have the 4 corner spins, and you have the 5th sites in the 4th dimension, which is here represented in the middle. So let's do a Gedanken experiment. Let's take a 2D centered kagome, okay? Like we're in 2 dimensions, we have the kagome lattice, and we put one site in the center. So you see this site, it makes a honeycomb lattice, and you have J1, J2 couplings. Now, take out these sites, and for the up triangle like this one, and this one, you make them going in 3 dimensions above the plane. And for the 3 others, you make them move in 3 dimensions below the plane. And you obtain this structure, which is a slab of the pyrochlore lattice in the 111 direction, okay? And but it's really a slab, so which means it's still 2 dimensions. You have, locally it's a slab of 3D pyrochlore, but you have open boundaries. And so if you look at the structure factor of the kagome lattice, you have these pinch points at low temperature. You can not go to very low temperature because you have onset of coplanar state, but still, when you are at intermediate low temperature, you have these pinch points corresponding to a sort of Coulomb phase in 2 dimensions. But then when you do the same simulations in this structure here with these additional center spins, you get these diffuse pinch points. So these diffuse pinch points, they correspond to the fact that when you add a central spin like this with open boundaries, the fluxes, you still have a divergence-free condition. So locally, you still have to respect that the sum of all the spins, that the local magnetization has to be 0. But the magnetic flux can go out of the system. It can exist through the top surface or through the bottom surface. And by exiting like this, you get these diffuse pinch points. So which are really reminiscent of the pinch points, but they get broadened because they can exit the systems locally. Now, if you do the same thing from 3D to 4 dimensions, imagine that you have a 4th dimension where the central spin go out. So they go out positively for some of the tetrahedron and negatively for the others. You can do field theory of this 4-dimensional lattice, so in 4 dimensions, and you get sharp pinch points. And then when you do this field theory or simulations of the 3D one, centered pyrochlore, you see these broad diffuse pinch points. So it's the same physics because, so our centered pyrochlore lattice, it really looks like a slab of a 4-dimensional pentacoron lattice. And because it's a slab with open boundaries, these open boundaries allow for the flux to exit it in the 4th dimension. And this exit of flux creates diffuse pinch points. So this is, so this is one explanation. This explains why we have these diffuse pinch points here. Another way to see it would be also to see this central spin that you have here as a kind of local charge. And this local charge would also play the role of disturbing the divergence fecundation and also create diffuse pinch points. There are 2 alternative ways to understand that. Yes? Yeah. So we have so in Monte Carlo we have checked. So this is Monte Carlo, and so when you make a cut, you actually obtain exponential decay. It's exponential decay because of this. So because the flux, you have the divergence condition locally, so you have 0 magnetization on all centered tetrahedron when you make the sum of the 5 spins. But because the flux can exit through the 4th dimension, you get exponential decay. Another way to see it is that if you see the central spin, so if you see the pyrochlore 3D lattice as 3 copies of U1 gauge field theory, then the central spin, you decompose X, Y, and Z component as 3 scalar charges. And these scalar charges act like a local disturbance and locally break the divergence condition. And so by breaking it, you get exponential decay. And so it is not a Coulomb phase. It's a kind of a 3D slab of a 4-dimensional Coulomb phase. But because of the open boundaries, you don't have algebraic correlations. And this was my intermediate slide to check how much time I have left. I started at what time? 10 minutes? Well, then I will give you a very short overview, maybe just an introduction about the other story, which essentially will be introducing the people and give you a story about reentrance. So this is a separate story. It's about pyrochlore. It's a paper that we published recently, last year. And the common point between those 2 stories is that it's also a collaboration between, basically we have 2 very smart students, so Darren Pereira on the theory and Daniel Yen on the experimental side. And it's also a very nice collaboration between chemists, experimentalists, and theorists to try to understand the phenomenon of reentrance in pyrochlores. So I will just give you a hint about this. But first, what is reentrance? As you know, a very general thing is that when you take a system, you cool down the system, you go from paramagnet to ordered phase. You always go towards something which is more ordered. But actually, it's not always the case, and you can have exceptions. And exceptions are, for example, the Rochelle salt. So I found, I think, the first experiment on Rochelle salt that measured this reentrance in Helvetica Physica Acta in 1939. And if you measure the electric polarization of this Rochelle salt, as you cool down, you have 0 polarization, then you have an onset of polarization, and the polarization disappears. So this is a phenomenon of reentrance. Like you have disordered phase, long-range ordered, and disordered phase again. This has been studied in many toy models in the 60s, and you can find a nice overview of this physics in this book here, or in this paper of Azaria, Dieppe, and Giacomini. And this was always related to some extensive degeneracy at low temperature. Like you have a special point with an extensive degeneracy, and this special point will give rise to reentrance. Then it has also been seen in modulated phases, where the competition between the stripe phase and the disordered phase with some intermediate pattern in between. And you have also quantum fluctuations. So that's a thing that if you have a quantum system at low temperature and you increase the magnetic field, then the quantum fluctuations might melt the order and lower the transition temperature. But as you turn the magnetic field, the system will become more classical, the quantum fluctuations will be less strong, and the transition temperature will increase. And as you see here, I've moved from a reentrance along the temperature to reentrance along the magnetic field. But both of them are reentrance. Okay? Reentrance is you take a parameter, you change the parameter in the temperature magnetic field, and you go from disordered to ordered to disordered. This has been observed in many different frustrated systems, on simulations on triangular and Kagome lattices, and in experiments also on pyrochlore and KTIF systems. And our point here will be just to give you a hint of explanations of this mechanism. And to do that, we will do it on erbium stannate. So erbium stannate is a material that has been well parameterized a few years ago with a complicated Hamiltonian, nearest neighbor anisotropic Hamiltonian, but it's well parameterized. So we know the details of this material here, and we know it orders into this antiferromagnetic state, which is six-fold degenerate. So that's all you need to remember now. You have pyrochlore lattice, well parameterized Hamiltonian, and six-fold antiferromagnetic degeneracy. And what we did, so we had chemists that were able to synthesize a single crystal of this material. So by doing a single crystal, that means that we can tune the magnetic field in different directions. And this was very difficult because for a very long time, single crystal of the standard pyrochlore was impossible. So that's what really allowed us to study it, because it was the first time that we could have single crystal of erbium stannate. Then Daniel did specific heat measurements, so with short pulse or long pulse cooling. And you see that we have a nice peak at low temperature in zero field. And as you increase the magnetic field, you see as this peak goes up, goes up, goes up, and then at some point it starts to go down. So this is the phase diagram that you obtain. And so the only point to remember here is that we have a frustrated system pyrochlore. We have put a magnetic field in three different directions, 100, 110, and 111. And in every case, we see a reentrance. So as we increase the magnetic field, first direction goes up, then it goes down. Here it goes up twice, and here it goes up once again. But every time we have reentrance. And when we do Monte Carlo simulations of that, we can see, so we don't have a quantitative fit, but qualitatively, we have the same phenomenon. Monte Carlo shows one reentrance here, two reentrance here, and one and the beginning of a second one here. So which means that classical Monte Carlo can reproduce the reentrance phenomena in erbium stannate, not quantitatively, but we can reproduce the physics, which means we can use Monte Carlo simulations to try to understand the mechanism behind reentrance here. And And to do that, we're just going to do it here for the sake of time. I'm just going to do it in the easiest case of 100. So this is the spin configuration in the ground state of one tetrahedron. And here what I'm going to do is increase the magnetic field. So the value of the magnetic field is given here. And here you will see this dot increasing. And in particular, look at what happens when you cross this boundary between the two. So the magnetic field starts to tilt the spin as you increase. So at low field, you have 6 degenerate states, but as you increase the field, these 6 states become less degenerate and they form only 2 degenerate states because they merge 3 by 3. And at higher field, you only have 1 state, which is a polarized one. And the thing is, at this transition temperature, what happens, if you do spin wave theory, you can see that the lowest band at this temperature, so look, at 0.8, this field is given here. At 0.8, you have the lowest band that touches it, you have flat modes, and then it disappears, it goes up, and then it comes back at 1.6 for the last one. But so the point is, around this point here, because you have merging of ground state, this merging of ground state creates soft modes. These soft modes means that you have a higher entropy at this point, which means that this state here has a higher entropy than for lower field and for higher field. And because of that, this state is more stable at finite temperature, and that's why you have a reentrance phenomena above this phase transition here. And so one point here that we want to say is that when you see reentrance in a magnetic field at finite temperature, this might be the indication of a 0 temperature phase transition between 2 different phases coming from the soft modes emerging from this competition between the 2 states. And I'm going to conclude with that. This phenomenon is the same one that you have here and here. Here you have a slightly different one where this, you have these soft modes, but then you have a change of 3 different ground states here very fast. And then here, you have different type of soft modes. So I'm not going to go into the details here for lack of time, but in all cases, the reentrant is connected to the appearance of soft modes and quite frequently can be attached to a zero temperature phase transition. And I thank you very much for your attention.
Thank you very much, Ludo. We have some questions.
About the phase diagram that you had in the first part of your talk, the diffused ferromagnet that you have, is it really a numerical artifact, or should I believe that this is a separate phase? And my next question would be, what do we know about the triple point?
This point here? Yeah. So you mean what, this diffuse here? Or?
No. Your PF phase, which I...
Yes. PF phase, yeah, with a partial ferromagnet.
This is a phase.
This is
it's not like a numerical artifact, or maybe...
So it's a phase. It's continuously connected to the ferromagnet because it has the same broken symmetry, which is a Z2, which is a broken symmetry. Then the only difference is that the ferromagnet, all of the 5 spins are really long-range ordered. The partial ferromagnet, the spins on the outside start to have some fluctuations, and so you have some stronger fluctuations. So the bright peaks coexist with stronger fluctuations. But so it is a real regime, I would say. So it's not a distinct phase to this one because it's the same broken symmetry. Between the two, you will have a crossover, but still it has distinct signatures. And then this triple point actually is not really a triple point because this is a phase transition and this is a crossover. So this here, it will just be maybe a point of large fluctuations, thermal fluctuations, but it's not a proper triple point.
Thank you.
Okay. Any other questions?
Hello, some online.
An estimate of the ordered moment in the manganese MOF.
Excuse me?
You have an estimate for the ordered moment in the manganese MOF.
So I know that the effective magnetic moment is of the order of 6 μb.
That's huge, but there is a proximate QSL above the order. So I'm wondering how much is the ordered moment reduced? That would say something about the frustration.
Right now we don't know. So that's the thing that so the reason why we didn't study explicitly the long range order at low temperature is because experimentally we don't know exactly what it is. Because the problem is that the MOF, the metal organic frameworks, have lots of hydrogens. Hydrogens absorb neutrons, so we don't have access to really neutrons to see the long range order. So and the phase seems to be mostly antiferromagnetic at low temperature. So we don't know the range of the ordered moment.
But for example, what is the entropy at the transition?
The entropy is finite. I don't have the value, but it's not like a small negligible value. It has compared to R log 6. I think it's R log 6. There is a finite residual entropy at the transition.
13.
It's been 5 earlier, so it should be R log 6.
R log 6. Sorry.
Okay. Andre?
Yeah. Hi, Ludo.
Yeah.
Thanks for the nice talk. Actually, I wanted to ask you the same about the entropy in the ordered state. But the second question would be, what about the entropy correlated to this short-range order? So how much entropy is there released? I guess you have some 0-point entropy. I mean, from this broad peak at high temperatures.
The entropy I was talking about, the finite entropy was really at the transition.
Yeah.
Below the transition, it's disappearing quite quickly.
What about the entropy related to the broad peak? I'm just wondering how much.
We don't really have a.
You're showing the broad peak, right?
Yeah. I'm sorry. I can show you the.
I'm wondering whether you have some degenerate state, right?
So we will have degenerate state.
Yeah.
But we don't have a plateau, so we don't see a plateau in this system.
Okay.
But the value of the entropy at the origin of the broad peak is actually pretty large. It's like if you divide like a R log 6, it's more in the upper half than the lower half. So the residual entropy in the regime of the broad peak, it's pretty large.
Okay, and then maybe a short question. Do you know what is the origin of the ordering? So what?
We don't know yet. We need to
direction?
do some more simulations. But so experimentally, basically, we need to deuterate the metal organic frameworks to be able to do neutron scattering. But that's expensive, and that's a whole different project. And numerically, we need to do it, but we need to add basically dipolar interactions. Because if we estimate the dipolar interactions, they are pretty small compared to the exchange. So
Exactly. Yeah.
exchange QFS temperature is 20 Kelvin, dipolar is of the order of a couple hundred millikelvin. So it's a factor 2 between the two. But 100 millikelvin, that's the order of the transition temperature. So we will not be surprised that the long-range dipolar interactions induce this long-range order, but we don't know yet.
Okay, you can also have some other anisotropies, I guess, even though the system is really symmetric, right? But it's still that experimentally you usually get also other anisotropies.
It is possible to
like
have
single ion, you know,
to have a local. So
like second order effect, yeah.
Yes, exactly. So it is possible to have a local z-axis or XY anisotropy, small one because it's manganese and it's a half-filled one, but it's still possible. J-free coupling, we tried to play with that, but it didn't really match the experiment. So we don't expect it to be only J-free exchange. But anisotropy is a possibility.
Okay, thank you.
All right. Do we have more questions? Online audience?
Hi, I had a question.
Yeah.
This is Pujari from IT Bombay. This diffuse structure factor, should I think of it as intermediate temperature physics, or it goes all the way down?
So this structure factor here, it's really low temperature physics. So if we do the simulations, that will be the structure factor you get in these temperatures.
Okay. Okay. Thank you.
And it's just so the thing that if you are at eta equals to 3, these pinch points will become broadened because of the thermal fluctuations. But when you are in this regime, this structure factor will actually qualitatively or even semi-quantitatively remain the same even when you increase temperature, because this is all relatively diffuse. So the increase of temperature will not modify the structure factor very much.
Indeed. I was wondering when you go down in temperature.
Sorry, I didn't hear, when you go.
When you lower the temperature, if you keep lowering the temperature, you still expect this to hold?
Yes, so these results are really at very low temperature, the lowest one we could get. And so when you lower the temperature, it's really persists like this.
I see. Thank you.
Okay. Do we have any further questions? If not, then let us thank Ludo and Marta one more time.
Thank you very much.